Welcome to this first video in the playlist on topology. In this video, what we're going to do is define what is meant by a topological space. Okay, so the definition of a topological space is one that a lot of people find very difficult to actually understand how it relates to the intuition behind what we're actually trying to capture. People understand what we're trying to capture, and they understand the abstract definition. What they struggle to do is understand why the abstract definition actually fits with what we were trying to achieve, and that's what I really hope to get across in this video. Okay, so we're going to start off by discussing what are we actually trying to achieve with a topological space. What is the motivation for what we're trying to achieve? And to illustrate what we're trying to achieve, I'm going to take the example of the two-dimensional plane. Okay, so topology is a part of geometry. It's a very, very important part of geometry, but it's not all of geometry. It's almost capturing something that is more fundamental than more fundamental than geometry. It's a very fundamental part of geometry. Okay, so we're going to be working with the two-dimensional plane, so I'll just draw my little two-dimensional plane here. Okay, so what I want to do then is I want to create a mathematical structure to represent my two-dimensional plane, to represent some sort of properties of the two-dimensional plane here. Now, the most foundational mathematical structure, the crudest mathematical structure that I can get for my plane here, is just going to be a set of elements where the elements are representing points on this plane. Okay, so the crudest mathematical representation that I can get then of my plane, which I'll call capital X here, is just going to be a set. Okay, and all the symbols in this set are going to be representing points. So I might have a point here on my plane. I'm going to give it the symbol P, and I'll put P into my set. So what I'm fundamentally doing here is I'm going through every single point on this two-dimensional plane here and giving it a symbol to represent it, and then I'm sticking it into this set. Okay, and that's going to be my mathematical representation of the plane. That is the crudest possible thing I could come up with to represent the plane. Okay, and then what can I do? Well, I can do set theory. Okay, that's pretty much all I can do then with this. So I can ask things like how many elements are there in this set to gain some sort of idea of how many points there are on the plane. So I can ask, is this going to be countably infinite? Is it going to be uncountably infinite? All of those sort of questions I can ask. Okay. In addition, you can set up functions using this. So for instance, an example would be, for instance, this plane. The points of this plane might all have a temperature. Okay, so I could set up a function which we might call, what should I call it, f, which could map this set x onto the real numbers, okay, specifically the positive real numbers, if we're working in Kelvin rather than at degrees Celsius, and it would then ascribe to every single point the real number, which is the temperature. Okay, so not only can we ask questions like how many points are there in this set, we can also build functions going from this set to some other mathematical structure, and this might capture something that is useful to physicists. Okay, so for instance, capturing the concept of temperature at each point in the two-dimensional plane. So we can do that as well. But we don't at the moment have much structure at all on this actual set here. It is just a set of points, okay? It's just a set of symbols at the moment. Now, this plane has a lot more structure than that, okay? The plane has notions of, we can take a ruler and measure the straight line distance between 2 points. Okay, now I don't want to define a distance on this set. You can do that, but I want to define a weaker notion on this set firstly, and that's going to be the concept of a topological space. Okay, what you can do is you can take this set and define what is meant by the distance between any 2 points in that set, and that's called a metric. Okay, and you turn this set into something called a metric space. Now, we're not going to discuss metric spaces, we're trying to discuss topological spaces. Metric spaces are really important in geometry. They're obviously capturing a concept that's really important for the two-dimensional plane here, but we want to go purer than that. We want to go more foundational than that. Okay, so I don't want to define a notion of distance on here. I want something more pure. Okay, and what do I actually want to capture then on here? I want to capture the notion of the points in this plane being connected to other points, okay, without putting a distance on here. Okay, so the points in this plane, they have a sort of order, they have a connected nature. Okay, so if you like, you can sort of imagine an infinitesimally close point to this point P that's connected to it, okay, more so than some point over here. So there's this notion of which points in this plane are connected to other points, okay, and I want to somehow capture that concept, and that's the concept that we are going to try and capture with the definition of a topological space. We are going to equip this set of symbols representing the points in our two-dimensional plane with a mathematical structure that will capture the notion of which points are nearby one another, which points are connected to one another, without putting the notion of a distance on. Of course, if you do put the notion of a distance on, if you do put a metric onto this set and turn it into a metric space, that gives you this notion of what points are connected to each other automatically. So that's a stronger structure. That puts the notion of topology onto the set automatically. But we want to try and do something weaker. We want to try and put the notion of connectedness on without actually putting on the notion of distance. We want to go purer, and that's the motivating concept for a topological space. Okay, now, why might we want to do this? What does this really capture? Well, imagine that this two-dimensional plane here is in fact made of elastic. Okay, so of some elastic material, then what I can do is stretch the plane out, okay, because it's made of elastic. And when I do that, I will change the distances between points on that plane. When I stretch it, points on that plane will be moved apart, and now their distances have changed. Okay, so the metrical structure will be going mad at that point. However, what points are connected to each other hasn't changed. The connected nature of the points, that hasn't changed by me stretching the elastic. Okay, so when you stretch the two-dimensional plane, this topological structure, and I'll start using that word now, that the topological structure is going to be this notion of connectedness, this notion of what's close to what else. That isn't going to change, even though the metrical structure, the notion of distance, does change. Okay, so we're going to try and create a mathematical structure that captures that fact. Now, the first thing to say is that it's absolutely easy if you're working with a finite set. Okay, so if you're working with a finite set, it's very easy to produce a mathematical structure that epitomizes how things are connected together. Okay, and let me demonstrate this. So if I have a finite set here, 1, 2, 3, okay, if I want to define how things are connected together in here, well, all I need to do is draw lines in between these symbols. So I can just imagine making an array of these symbols like so. And if I want 1 to be connected to 2, I could draw a little line between 1 and 2. And if I want 2 to be connected to 3 next to 3, I'll draw a little line between 2 and 3. And then if I don't want 1 and 3 to be next to each other, I won't draw a little line between those. Okay, so it's very easy to define this notion of what is connected to what if we're working with a finite set. We just literally, bluntly, draw lines between the elements. This is much more difficult when we're working with an uncountably infinite set, which is the nature of this set of all the points on the two-dimensional plane. Okay, But intuitively, the intuition that I would like you to have here, even though it's not rigorous at all, intuitively what you're kind of doing, this is the way I envisage it, is you're drawing little lines between points on this plane that are infinitesimally close to one another. And I know that's not rigorous at all. Okay, pure mathematicians won't like that. But intuitively, that's what this is capturing. It's capturing this concept that we can draw tiny little lines between this point and all the little neighbouring points that are infinitesimally close to it. So obviously there is no points which are closest to this point P. Okay, so infinitesimally isn't a rigorizable concept, but intuitively it does kind of make sense to think of these points that are incredibly close, closer than any other points, and then you're drawing little lines between this point and those points that are infinitesimally close. So that is the non-rigorous sort of intuition behind how we will do something analogous to this for this two-dimensional plane here. So we'll be drawing lines between the points and those points that are infinitesimally close to them. So really, intuitively, the way I envisage the topology on this is that we've got almost a grid like this, okay, where these lines here are going to be the lines in between infinitesimally close points, basically. Okay, so these little squares would have to become infinitesimally small, and then these are the points of the plane with the lines drawn in between them. Obviously it doesn't look like that, but if we could zoom into the infinitesimal scale, this is what I like to envisage it would look like. Okay, and somehow we need to capture that in a rigorous way, and that's what we're going to do with the abstract definition of a topology. Okay, right. So now that's my intuition of what a topological space is going to capture. Let's now do the rigorous pure maths of it. So what is the rigorous definition of a topological space? Okay, so the rigorous definition then of a topological space, well, fundamentally you start off with a set of symbols, so we'll stick with the same notation and we'll call our set of symbols capital X here. Okay, so we start off with our set of symbols, capital X here, and we're now going to equip this set of symbols with a topology, which is the structural feature that is going to capture this notion of which points are next to which other points. Okay, and I will call the topology tau. People use loads of different notations for a topology. Tau's a reasonably common one, so we'll go for that. Okay, and then the set along with this structure defined on it is then going to be called a topological space. So this thing is going to become a topological space once I've defined this tau structure, the topology on it. Okay, so the whole thing is the topological space. Tau here is what we will call the topology. So we need to define this structural feature on this set capital X, tau, which is going to be the topology on that set. And the set with its topology is going to be called a topological space. Okay, so what then is tau? What fundamentally is a topology? How do we rigorously capture this notion of what is next to what without putting a notion of a distance between points? Okay, so the way that we do it then is tau is actually going to be a subset of the power set of X. So tau is actually going to be a set containing loads of subsets of this set capital X. So tau is going to be a subset of what's called the power set of X. Okay, now I know this is probably now intimidating to you, so let me explain exactly what the power set of X is and what do I mean by tau being a subset of that. Okay, so let me draw a picture then. So we have our set capital X here. Okay, and let's say all the points in this set are in this box here, and I don't mean to imply that this box is necessarily the two-dimensional plane anymore. This is just representing my abstract set now. So we've gone abstract now. We aren't necessarily talking about the two-dimensional plane, although we will come back to the two-dimensional plane. At the moment, we're just talking about some abstract set, and that's the beauty of this, that this has universal applicability because it's just a definition on a set. Okay, we don't have to be talking about geometry geometry at all, okay? You can be talking about sets of totally different things that have nothing to do with the points on a plane or the points in three-dimensional space or n-dimensional space or whatever, okay? It just has to be a set, okay? And that's why pure maths is so powerful, because of course these structures, these logical structures that they dream up, can be applied all over the place. Okay, right, so it's just a set containing symbols at the moment. Okay, now, the notion then of the power set of X is, it is a set itself, okay, and it's the set that will contain all subsets of this set X. Okay, so this is a complicated set because the elements of this set are themselves going to be sets. Okay, so the elements of this set are all the subsets of our set capital X. So it's all capital S, where S is a subset of capital X. Okay, like so. So these S's are just subsets of capital X. So marking it on my picture here, this sub-collection of the points of the set X could be my subset capital S. And what you have to do is you have to come up with every possible subset of this set capital X. So you go through every possible combination of the elements of this set capital X that you could possibly dream up. You stick them all into a great big set. So the elements of this set will be subsets of capital X. And that is what is meant by the power set of the set capital X. So it's the set of all subsets of the set capital X. And I do appreciate that that's a difficult concept if you're seeing it for the first time, that the elements of that set are sets themselves. But after all, they're just symbols. They can be elements of a set. The elements of a set are just things, and sets are things, so they can be the elements of a set. Okay? Right. So now what we're going to do is we're going to take a subset of the power set of X. So tau, the topology, is just going to be a set containing subsets of the set capital X, but not necessarily all of them. It doesn't necessarily contain all of them, unlike the power set of X, which is why it is a subset of the power set of X. So the elements of tau then are going to be subsets of our abstract set capital X. So that fundamentally is what tau is. It's just a sub-collection of subsets of the set capital X. Okay, now it can't just be any old sub-collection though. Okay, we want this sub-collection to obey some incredible properties. Okay, we want it to have some beautiful properties that make it warrant study. Okay, so if it doesn't have some beautiful properties, then it's not really worth bothering to study. Okay, so if we're going to pay attention to this sub-collection of subsets of the set X, we want it to obey some beautiful properties. Okay, and those properties are the axioms of a topological space. Okay, so I'm going to state what properties we want this tau to obey if it is to be categorized as a topology. And if it doesn't obey these properties, then the blunt reality is that the pure mathematician says, no, you are not having the title of a topology, you are just a sub-collection of subsets of X, and I don't care about you. Okay, they just want to study things that are interesting, and if the sub-collection of subsets of the set X obeys these axioms, then it becomes interesting and it becomes known as a topology. And then if you stick that as a structure on your set X, it becomes known as a topological space. And pure mathematicians can prove all sorts of things about these topological spaces just from these three axioms being true. Okay, so what are the three axioms then that tau must obey? Well, axiom number 1 is a really simple one to understand. It concerns two subsets of the set capital X that you are always going to insist must be in tau. Okay, so whenever you've got something like that, it's always nice because it's incredibly easy to understand. Okay, so axiom number 1 says that the empty set, which is a trivial subset of the set capital X, it's the set where you take absolutely no elements of capital X. Okay, so it's the set that contains nothing. That will always be a subset. It's a trivial example, but it is always counted as a subset of capital X. So it will always be within the power set of capital X. If I start writing out the power set of capital X here explicitly, okay, one of the elements that I can always rely on being in here is the empty set, i.e. this stupid looking set that contains absolutely nothing. Okay, however, because that looks so stupid, mathematicians don't write it like that. Instead, they write it like so. They put the phi symbol, capital Phi, the Greek letter phi, to denote that, to make it look less stupid. Okay, so that will always be an element of the power set of X. Okay, and we're going to insist that it's also going to be an element of our topology, which is this subset of the power set of X. So we're going to insist that the empty set is an element of tau. Okay, another subset that we're always going to insist is going to be in tau is going to be the entire set. So this is another trivial example of a subset of the set capital X. Okay, so remember, a subset does not actually need to be a proper subset. It doesn't actually need to not contain all elements of the set. So the entire set itself is counted as a subset of the entire set. Okay, so there's another thing that we can always say is going to be in the power set of any set, the entire set itself, and in fact we're going to insist that that's going to be in our topology as well. So if I start drawing out a picture of tau here, this subset of the power set of X, it's going to contain the empty set and indeed the entire space. Those are two elements that you can always say will be in the topology because pure mathematicians insist that they must be there. Okay, they make it as one of the axioms that they insist a topology must obey to be called a topology. Okay, so those are always in the topology. Okay, now axiom number 2 and 3 are slightly more complicated than that first one, but they're still not that complicated. Okay, so axiom number 2 then. So axiom number 2 says if we have two subsets of the set capital X which are in our topology tau. Okay, so let, in fact I should have probably put for all, let's get rid of that let. So for all U1 and U2, okay, and people generally denote subsets of the set capital X that are included in the topology by U, okay, for historical reasons. So we'll have for all U1 and U2, and these are just subsets of the set capital X which are within the topology tau. Okay, so they're just subsets that are in here, U1 and U2 here. So for all U1 and U2 are elements of the topology tau, we insist that when we intersect those two subsets, so U1 intersect U2, the intersection must be another element of the topology tau. So adding that onto my picture, let's say that this green subset here is now U1, and let's draw another one on here. So here is my other one, this is U2, so I'll just colour them in. So we'll have U2 represented in red here, and I'll just make sure this is straight, yep. Okay, so these two, let's say, are both elements of our topology tau, so they're both subsets of the set X, which we have chosen to be within this subcollection of the power set, which we're calling the topology. Now, we're going to insist that if you intersect any two elements in here, so you pick any elements, any two elements from your topology, I'm going to insist that when we intersect them, I want you to have picked the topology so carefully that the intersection of those two, U1 intersect U2, which is, I'll just highlight it up in yellow here, this subset here, I'm going to insist that that also has to be in the topology tau. So you better have picked those subsets carefully if you're going to want this to be true. You can't just put two elements of the power set in, two subsets of the set capital X in, and not also put their intersection in. You must make sure that their intersection is in there as well. Otherwise you're going to fail axiom number 2 here. Now, of course, this very quickly extends, because if U1 intersect U2 has to be an element of tau, then what I can do is pick another U3, which is an element of tau, and say, okay, U1 intersect U2 is an element of tau, U3 is an element of tau, therefore, applying this property now to U1 intersect U2 and U3, I get that U1 intersect U2 intersect U3 also has to be an element of tau. Okay, do you understand what I've done there? I've said this is now an element of tau, okay, by this property, and if I have some further subset here, U3, which is an element of tau, then what I can say is because any two elements of the topology intersected together has to be another element of the topology, then I can intersect U1 intersect U2 with U3, and I can say that that also has to be an element of the topology. So once this is true, it also follows for three things intersected together that they have to be in the topology, and therefore you can extend this in fact to an arbitrary finite intersection. So follows from this that the intersection from I is equal to 1 to some n, where n is some finite natural number, okay, of ui also has to be an element of the topology if all these ui's are elements of the topology. Okay, so if you take a finite number of subsets in the topology and intersect them together, you have to get another element which is in the topology. I hope you understand how I've derived that from this statement. So axiom number 2 says this, but as soon as this is true, you can instantly just extend this to this statement here, that you can intersect a finite number of subsets in the topology, and that answer must also be in the topology. Okay, so that's axiom number 2 then, that if you intersect any two subsets that are in the topology, you must get another element that's in the topology. So you have to design this subset of the power set very, very well. Okay, and we're going to insist further. Okay, so axiom number 3 now. Axiom number 3 is probably the most complicated to understand. This now refers to unions of subsets in the topology. Okay, now here we got up to this statement eventually, that if you have a finite number of subsets in the topology and you intersect them all, the answer has to also be in the topology. With unions, it's going to be even more complicated. Not only are we going to extend this to infinite sets, but we're actually going to extend it to uncountably infinite sets. Okay, so let me write this out explicitly. So, we are going to have a whole bunch of sets from our topology, okay, so u alpha, where alpha is some subscript, so just like, or some index rather, so just like I had u1, u2, u3, u4, all the way up to un, alpha here is just an index, it's just a way of labelling up these subsets that are in my topology. Okay, the important point here is that I'm picking loads of subsets that are all in my topology tau. Okay, now we are going to insist that the union of subsets that are in the topology, so the union over alpha of all these subsets that are in the topology must also be within the topology. Okay, and that alpha, that can be any index you like. Okay, and let me stress what this actually means. Okay, it could be a finite index, it could be 1, 2, 3 all the way up to n, okay, in which case this looks like this, or it could be an infinite index, so it could be the infinite natural numbers, so it could be the intersection of u1, u2, u3, u4, and you could go on and on. But it gets even worse. It doesn't necessarily have to be a countably finite index here, okay, sorry, a countably infinite index here. Okay, so usually we index things with the natural numbers, but what I can do is instead index it with the real numbers, and I still want it to be true. So for instance, I could I could get a whole bunch of open sets and label them all up with a real number. Okay, so I could have u 2.1, u pi, u the square root of 3, all of these. I could come up with open sets that are being indexed with all the different real numbers. Okay, and the important message to take from that is that this will be an uncountably infinite set if it's going to be indexed with the real numbers. Okay, and I'm still going to insist that this is true, that when you union them all together, you end up with something back in the topology. So you can union together finitely many subsets in the topology. You can union together infinitely many subsets within the topology. And whatever you do, you will always get another element of the topology. And let me stress it again. It can be an uncountably infinite number of subsets in the topology, or uncountably infinite subsets, uncountably infinite number of subsets from our topology. Okay, and when you union them together, you must get another element of the topology. Okay, so those together, those three properties are the three properties that we are going to insist that this subset of the power set of X must obey if it is going to be called a topology. So if and only if your subset of the power set of X obeys these three properties, does it get the title of being a topology. And when you stick this as a structure on your set capital X, that then is called a topological space. Okay, right, so we'll have a break there whilst you digest that information, and in the next video what we'll do is a few very basic definitions, the definition of an open and closed set, and then what we'll do is the big meaty question, which is why does this abstract definition actually capture this intuitive notion of what is next to what in this set capital X?